Hello everyone. In this video, we are going to start our first lecture on probabilities. So we're going to work on some basic definitions and some basic formulas. The first definition we have to work on is an experiment. So when we say experiment, we mean a measurement, an observation. And the measurement or observation or the experiment has to involve randomness. If the result of that is 100% predictable ahead of time, then that's not what the probabilities is interested in, right? If I know that, for example, I have a dice, and when I throw the dice, all 6 faces of the dice are all the same number. Let's say all of them are 3. And then I said, okay, what is the outcome? Well, of course, the outcome is going to be 3. So there is no chance, there is no randomness. It's completely predictable, right? So it's all about the cases that we cannot predict. Now, a single time that we do that experiment is what we call a trial, and the result of that trial is what we call an outcome, right? So let's say it is a coin and we toss it up in the air and it either lands heads or tails. So that is one trial of that experiment of throwing a coin, and the outcome, which is either heads or tails, that is the outcome. Now, the set of all possible potential outcomes of an experiment is what we call the sample space, right? So again, for the coin example, the sample space is what? Is basically, which is shown by letter S typically, or universal set. This is gonna be what? Heads or tails, correct? So that's for the coin example. Or let's say when you throw a dice, S is what? 1, 2, 3, all the way to 6, correct? So that's the set of all possible outcome. Now, if S has finitely many outcomes, basically you can determine, you can count, it's countable, you can count how many potential outcomes it has, and they are all equally likely. So let's say when you throw a dice, your dice is what we call a fair dice, or your coin is a fair coin. So the chance of a head showing up is the same as a tail showing up. Or for a dice, the chance of numbers from 1 to 6, each one showing up, is the same. They are basically equal, right? It's a fair experiment. It gives the same chance to all potential outcomes. Then for a specific event, for a specific outcome, the chance that A is happening is what? The probability of it, right? If we want to mathematically use the term probability instead of chance, the probability that A is happening is what? Is the number of times that A occurs divided by the number of all trials. So that is the first and basic definition of probability for an event. The number of times that event occurs over the number of the times that all potential events, all different trials have different outcomes. Clearly, that number should be between what? 0 and 1, correct? Because A cannot happen more than all of your trials are happening. So, for example, when you throw a dice, what is the chance or what is the probability of landing 6? So landing 6 here is your event A. And I'm asking for P of A, which is the outcome of the dice is 6. Well, based on what we know from probably intuition, you say, well, if the total number of trials is n over 6 in general could be the number of times that 1 shows up, 2 shows up, 3, 4, 5, and 6. So you might say it should be what? 1 over 6. But is that the case really? I mean, here, this is what I'm going to do for you. I'm going to simulate this throwing a dice for you. and will count the chance of landing 6. Well, how do I do that? So if you know in MATLAB, the command randi will generate an integer number for you, which is between 1 to a maximum number, let's say 6 here, and all you need is to say how many of that you want. So let's say here I only want one random number. So you see, first time you call it, it gives you 1, next time it's 2, next time it's 4, 6, 6, 1, 6, 6, 3, 5, 1, 3, right? And hopefully, let's see if it gives us a 2. Seems like it doesn't want to give me a 2. Ah, there we go. So this is what we're going to do. We are going to write a simple code here. And in this code, I'm going to basically start some counter, okay? And this counter is going to be zeros of 6 and 1. So what is this counter? This is the number of times each one of the numbers 1 to 6 has shown up in the outcome of a dice. Now what do I do? For I equal 1 to n, and n is the number of trials, is the number of times I'm going to throw the dice. And I decide that as a parameter. So let's say 1,000 times. Go ahead and do what? Generate a number, and this number is equal to randi of 6 and 1, which is what? A random integer between 1 to 6 and only one number. And then what? Based on this number, do what? Or you can use an if statements, right? So switch case what? Hopefully you remember my video on the switch case, right? Switch case otherwise. If you don't, please go ahead and look at the structure, okay? So what you do, you write switch. Your variable can only take on a few number of data points. You have specific cases, and otherwise is for the case that it is showing something that it shouldn't be showing, okay? And then you perform a command here. So you say switch case what? Number is 1. I want you to add to the count number 1 to be what? To be whatever it was plus 1. Because if it shows 1, the first entry in that count is the number of times 1 is showing up. So I'm going to add 1 to it. Similarly, I'm going to go, if it's count, if the case is 2, I'm going to add 1 to the case of the count of 2, and then I will repeat that. I go for the case of 3, I go for the case of 4, 5, and 6, correct? And I will add to the counter for that specific number. And finally, I consider an otherwise, although it should never happen, but otherwise, which means the number generated is not 1, 2, 3, 4, 5, 6. I will what? I will return, which means I'm terminating the code, and there is something going on here, right? And then end. Okay, so I do that, and then what I will do, I will plot for you what? I will plot for you the set of all outcomes, which is 1 to 6. I will plot that versus the count. But count is the number of times each one occurred, and we have to divide all of them by the total number of trials, which in this case is n. So I have to divide that by n, and that will give me what? X label is going to be outcome, and Y label is going to be P of A, correct? So here we go. And I call it probability dice demo. So if we run that, it should, okay, let me use the bar command. There we go. You see that almost they are about 1/6 or 0.167, but they are not exactly all equal. It seems like one appeared less than the others, two appeared a little bit more but less than the others, 3, 4, 5 close, right? So this is when I performed 1,000 throwing of dice. Now what if I decide to change the number? What's going to happen? So here, if I, instead of 1,000 trials, I just make it 100 trials. Now look. You see, now it does not look like the dice is fair. It seems like it is favoring 4 more than the others, a little bit more 6, and then 1 maybe less. And since it's random, if I do it one more time, I will get a different distribution. You see, now it seems like it is not too bad with 1 and 2, 3 still, right? That's the nature of randomness. It's not going to give you the same result every time that you try it. So if that is the case, how do I get up with a number here, right? If I change my number of trials, and if I do even with the same number of trials another time, the whole experiment, I will get a different number really, right? For each one of the events. So where did I get up with this 1/6? So this 1/6 is theoretical. It can be close to the reality when you do lots and lots of experiments. Okay, so let's say now I make it what? 1,000,000 times throwing the dice. Now, ideally, it is like instead of throwing it 100 times, that you saw all those variations, when you did it 1,000 times, it was closer to all of them being the same. Now look, when I make it, for example, instead of 1,000, let me make it 10,000 first. You see they are closer. You see, if I add one more 0, they should be even closer, because all of those randomness in the experiments will kind of cancel each other, right? So one time one is more, 1 times 1 is less, but when you add all of them together or do it a bunch of times, they kind of add up together to get close to the same number, right? You see, so now if I add one more, you see, now they're almost all getting at the same level of 1/6. So if you really want to get these numbers, you have to do your experiment a large number of times so that the effect of randomness is basically fading in the final number that you are trying to calculate, okay? So please keep that in mind. Good. Now, it is obvious based on the definition we had that the probability of the event, if the event is the whole S, is the whole basically sample space, it is going to be 1, of course, because if the event is whether the dice is landing 1 or 2 or 3 or 4 or 5 or 6, well, of course, it is going to be one of these, so the chance of it happening is 1. Or the chance of the coin landing a heads or a tails is going to be what? Of course, a 1, because that's all possible solutions, and the chance that nothing is happening is 0, right? So the chance of the empty set or empty event is 0, okay? Good. Now, there are more to these definitions of probability, the way we define it. There are more formulas, more theorems that we need to talk about. One case is if you have 2 events now, A and B, and they are mutually exclusive. What does that mean? It means they cannot happen together, or the intersection of those 2 events is the empty set, or the chance of them happening at the same time, the joint probability is 0. If that is the case, then the chance of either one is happening is going to be what? The chance of one plus the chance of the other. So again, here, the two events should not happen together. They are mutually exclusive. Then what is the chance that either one happening, either A happening or B, doesn't matter which one, just one of them at least happening, or both, the chance of that union or is going to be summation of the chances. Okay? Now you might say, like what? What two events can be mutually exclusive? And I can tell you, for example, for the example of the dice, one is going to be that A shows up as the outcome. The other, for example, could be the chance that 4 shows up, right? When you throw a dice, it's impossible that you get 1 and 4 at the top of the dice at the same time. It's either 1 or 4, right? Or the others. It's impossible to have both of them at the same time. So it's what we can say the chance of landing 1 or 4, they are what? These two events are mutually exclusive. So now if I say what is the chance that the outcome is what? 1 or the outcome is what? 4. You say that is the chance of it is 1 plus the chance of it is 4, and since each one of these independent events for a fair dice is 1/6, so the chance that you see one of these is going to be what? 1/3. Okay, so this is your mutually exclusive. Now, not all events are mutually exclusive. If they are not, which means they can happen at the same time, or their intersection is not empty, then the chance of their union, or the fact that one of them happens or the other or both, is going to be sum of the individual probabilities minus the probability of both of them happening at the same time, or the joint probability. Okay, this guy is what we call the joint probability. So the probability of union is going to be the probability of both of them added together minus the chance that they can happen together. Like what? So say we have a mechanism to generate a random number between 1 to 20. We want to know what is the chance, what is the probability that this random number that you generate is divisible by 2 or 3, right? So the event is, we have two events. One is X mode, or mode of, let me write it the way MATLAB does. Modulus of X and 2 equals 0. The other case is modulus of X and 3 is equal 0, right? And I'm interested in the probability that it's either A or B. So I'm looking into P of A union B. But first, what is the chance of each one? So what is P of A, right? If I generate a random number between 1 to 20, what's the chance that the number can be divided by 2? Well, all of the numbers that are even can be divided. So from 1 to 20, 2, 4, 6, all the way to 20, right? Half of the numbers are basically can be divided by 2 without any remaining terms. So the chance is 1/2, because 1/2 of the numbers qualify for the condition. What about 3? Well, for the 3, we have 3, 6, 9, correct? And then we have 12, 15, and 18. So there are 6 numbers out of all 20 that qualify. So it is going to be 3/10, right? So this is like 0.3, this is like 0.5. This is the chance that A is happening, half. The chance that B is happening is 0.3, right? Good. Now the question is, what is the chance that they both happen together? What does it mean? It means that what is the chance that a mode of x and 2 equals mode of x and 3, and that is also equal to 0. So the number should be divisible by 2 and 3 at the same time. And so it means the number should be divisible by 6. And the numbers that qualify are 6, 12, and 18, right? That's all it is. So you have 3 out of the 20 numbers that qualify, and if you multiply by a 5, right, it is going to be 15%. So 15% you have the chance of both of them happening at the same time. Now the question is, what is the chance is either one or the other happening? Well, based on what we have, it is going to be summation of the probabilities of individual terms minus the probability of joint. So this is going to be 0.3 plus 0.5, that's 0.8 minus 0.15, that is going to be 0.65. Right? 0.65 is the chance of that to happen. And here again, you can do the same, use the same code to experiment that. And what I will do for you here is I'm going to look at just a counter that I start at 0. I generate a number, random number, integer with a max of 20, so it's between 1 to 20. And then what? This is what I will do. I generate the random number, and then if mode of x and 2 equals 0, or mode of x and 3 equals 0, right? Or, right? It's one of them or the other one. If that is the case, then I will add 1 to that count. Right? Done. Right? Now here it says use the shortcut or, fine, we can use that. And if that's the case, now all I want it to tell me is basically count divided by n. That's all I want, the probability. Just give me the probability, let's say how much it is going to be. Right? So here, if I do it, seems like I had an error. Right? It says what is x? Of course, because we called it num, not x. So here we go. You see the number is what? 0.649. It's very close to that 0.65 that we had, correct? It's very close to that. And this is only using 10,000. Now, if I reduce the number, my number is going to be deviated from that because there is a lot of randomness going on. So with 1,000, I'm not going to get as close. With 100, it's probably off. But if I go ahead and add a bunch of zeros, like here, make it 1,000,000, I expect my number to be what? Very close to 0.65. You see? So whatever we calculated is demonstrated through simulation as well. Good. So hopefully it is clear what we are doing. Good. Now, what else? There is another thing we have in probabilities. It is called complement. What is complement? Complement means that instead of A is happening, A is not happening. Okay? So the chance that A does not happen can be considered as what? 1 minus the chance that A is happening, okay? So A complement means A does not happen. Where does this formula come from? It directly comes from this mutually exclusive case here. Because A and A complement are mutually exclusive. Either A can happen or it can't. There is no intersection between A and A complement, right? So A intersection A complement is equal to empty set. Therefore, P of A plus P of A complement, right, is going to be the same as the chance of their union, right? So here, let me expand this for you. So we have some more room. Okay. So P of A union A complement is going to be equal to P of A plus P of A complement, because there is no intersection. I'm directly using this theorem here. And what is A union A complement? That A happens or it doesn't happen. Well, that considers all possible scenarios. When you throw something, let's say a dice or so, it either happens A or it doesn't. So this is the same as what? The entire possible scenarios. And P of S, based on what we know, it is equal to what? It is equal to 1. So the summation of P of A and A complement is equal to 1. Therefore, P of A complement is 1 minus P A. Good? Example. If you throw a dice, what is the chance that the number that shows up is not a prime number? So in this case, it is easier to calculate what is the chance that X is a prime number. Or maybe since just it's 6 possible scenarios, maybe you can directly calculate a complement. But what is the chance that it is a prime number? Well, all possible scenarios between 1 to 6 where prime number is what? 2, 3, and 5. So the chance is 3 over 6. Therefore, right, the chance that it is not a prime number is 1 minus this number. This is 1/2. So the chance that P of let's see, A is defined like this. That was 1/2, and then the chance that a complement is happening, which is the number is not a prime number, which means it is 1 or 4 or 6. It is can be written directly as 3 over 6 or 1 minus the chance of A, which is also going to be 1/2 or 3 over 6. Okay, so this is the chance of a complement or A does not happen. Good. The next topic we have to talk about is conditional probability. That's the probability of event A happening if event B has already happened. So here, this term P of A event B, which you can see with this vertical line, this conditional probability is defined as or calculated by the chance that A of B can happen together divided by the chance that B has happened. This is how we calculate the chance of A happening given that B has happened, or conditioned on the fact that B is has already happened. For example, you say, let's say you have a pack of cards. You draw an ace from the pack of cards and keep it. Do not return it back to the pack of cards. You want to know if the next person comes in and he or she wants to draw another ace from the pack, what is the chance of that event, okay? So here, event B is person 1 has already drawn an ace from the pack. Event A is the chance of the second person drawing an ace from the pack, okay? So how do I find the chance of the second person drawing an ace given that the first person already did it and kept the card? So for that, I need to calculate P of B and P of A given B. So here, if we go ahead and calculate P of B, which is the first person drawing an ace, well, you know a pack of cards has 52 cards and there are 4 aces in it. So the chance for the first person to draw is 1/13. Now, what is the chance of A and B? What does it mean? It means the chance that the first person draws an ace and the second person draw an ace, both of them happening at the same time. Now here, it might actually be easier to directly calculate P of A given B by the nature of it, right? So let's see whether you get equality or not. So what is P of A equal B is? Because you know from here, if I cross multiply P of A given B, the joint probability is P of A given B times P of B, correct? So would that here hold? Would I get an equality in this case? So P of A given B is very easy in this case. Why? Because you had 52 cards. You drew an ace and kept it. So now you have 51 cards. And in these 51 cards, there is only what? 3 aces left. So this is your chance of the second person getting another ace. 3 over what? 51. So from here, if you look at these two numbers, the chance of A joint B or intersection B is going to be the product of the two terms. So there's going to be 1/13, or we can say 4/52 times 3/51, correct? Or it is 12 over the product of the two, which is this is 2600, so it is going to be 2652, right? So, or as I said, if you simplify this by 1 and 13, then you will get 3/510 plus 153, which is 663, right? Make sure 13 times 51, 663. That's right. Now, can I get such number here? Does this number make any sense? Does this number make any sense? That the chance of both of them happening is basically 4 times 52 times 3 times 51. Does that make any sense? Well, what is that really? This is the product of two terms. The first one is clearly the chance of what? The chance of B, as we calculate it, right? 4/52. What is this one, 3/51? This is the chance of A alone, correct? And A is what? The second person drawing an ace from the 51 cards that are left. So it seems like it says P of A intersection with B is equal to P of A times P of B, right? What does that mean? That's the next topic here, actually. And that is if the joint probability of two things happening at the same time is the product of the two terms. We call those two events, we call them what? Independent. Okay, if that's the case, we can call it independent. Now, is that the case here? Keep in mind, A means first, B means first person drawing an ace from 52 cards. A means the second person drawing another ace from 51 cards. Are these two independent from each other? And the answer is yes, they are. Because I have already considered the effect of the person keeping the card, right? So it is already reflected here. There is no independence between these two anymore. The first person has basically 52 cards, and he drew somewhere here an ace, right? Let's say an ace of diamonds, he took it off. Now it is down to what? 51 cards. And the next person is going to take another one, let's say, correct? So are these two events, this is event B, this is event A, are these two events independent from each other? Absolutely. They have no interaction now, correct? Because I am now considering this A a separate event. Now that I'm only down to 51 cards, B happening and A happening, both of them at the same time, it's going to be the chance of B times the chance of A, correct? So because in this case these two events are independent, if I had to calculate the joint probability, I could also do it by what? By multiplying the chance of A and the chance of B, or I could calculate it through what? Through the conditional probability. So if I wanted to calculate P of AB, instead of directly by intuition, another way I could do it was this. I could say P of A given B is P of A joint B divided by P of B, and P of A joint B was P of A times P of B, because these two events are independent from each other, divided by P of B. And since you can simplify these two, the chance of P of A given B is going to be the same as what? P of A, which in this case it is clearly what? 3/51. Okay, so here I mentioned both of these topics at the same time. One was conditional probability, two was what? Independence of two things. So two events are independent if the joint probability is the product of the two, or if P of A given B is the same as P of A. In other words, whether B has happened already or not, it has no effect on A happening. And the other way around, P of B given A is the same as P of B. So the happening of A has no effect on happening of B. These two do not depend on each other. They have no independence. Okay? They have no dependence, I'm sorry. Another example we can look is this. If you throw two dice, what is the chance that one of them lands a 2, the other one lands a 3? Well, the two dice have no connection. They have no physical interaction with each other, right? So if one of them is to land a 2 and the other one to land a 3, these are two independent trials, two independent things, and the chance for this A happening is 1 over 6 because it's one of the 6 numbers, and the chance for B is also what? 1 over 6 because it's again 1 out of 6 numbers. So the chance that one of them does this and the other one, and means intersection, the other one does 3, it is P of A times P of B, and that is 1/6 times 1 over 6 times 1 over 6, which is 1 over 36. Okay, so hopefully the idea of independence of events and conditional probability is clear. Now there is another idea which is related to these, especially the conditional, and that is called total probability. What is that one? Well, if you have event A and the chance of event A happening does depend on B, C, and D. So you have conditional terms of P of A given B, P of A given C, and P of A given D. Then the chance of A happening is calculated by P of A given B times P of B plus P of A given C times P of C plus P of A given D times P of D. Okay, so B, C, and D are the things that their happening will affect the happening of A. So A depends on them. There is a condition of A on B, C, and D. So if I know what is the chance for B, C, and D happening and what are the conditional probabilities, I can add these product terms together to get what? The chance of A happening. Okay, and what's an example of that? So here it says there are 3 machines in a company, machines A, B, and C. They each manufacture chips in a company, an electronic circuit. Machine A, or line A, generates 25% of the microchips, the other one B 35%, and C generates 40% of the electronic components. The chance that you find a defective chip in line A is 5%, in line B is 4%, in line C it is 2%. Where did they get these numbers? By a lot of observations, by collecting samples over and over and over, and then coming up with some average or expected number. So given the chance of defectives in each line, and given that how much each line is producing chips, the question is, if I go ahead and give you a random chip, okay, what is the chance of that random chip being defective? So A here is what? Is a random chip being what? Being defective, correct? But that depends on what? Depends on whether it's coming from line B, C, or D. So event B is a chip from machine B, or let's use a different notation here. So I call this event D, if you don't mind. B is a chip from machine B is defective. A is going to be a chip from machine A is defective, and similarly I will have stuff for machine A and machine C. So let's see here, this is one and this is 1. See if I can do a better job. There we go. And there we go. Okay, so A is a chip from machine A is broken, and C is a chip from machine C is broken or defective. Now, what is it that I'm interested here? It's the probability of D, the chance that one chip is defective in general. Doesn't matter which machine. How can I find it? Well, I say it is P of D given A times P of A plus P of D given B times P of B, and finally plus P of D given C times P of C. What's the meaning of that? It says the chance of a chip being defective is equal to the chance of a chip coming from line A. So this is, if you have a chip, what's the chance it is coming from machine A? Well, based on the percentages, we know A makes 25% of the chips, so this chance is what? It is 25 over 100, right? This is the chance that a chip coming from machine A. What's the chance that a chip coming from machine B? That is 35%. And what's the chance that it is coming from machine C? That is 40%. So the conditionals are the chance of a chip in general being from one of the lines. Now, what's the chance of A, which is a broken chip from line A? Well, that is 5%. For machine B, the chance of a chip being defective is 2%, and for line C, it is 4%, right? These are the numbers I have, or 4 and 2 actually. So this is 4, this is 2. So now all I need is to multiply and get the numbers. So it is going to be 10,000, because they all have hundreds. This is 5 times 25, so it is 125, plus that is 4 times 35, so this is 140, and the last one is 80, correct? So the final solution is going to be 345 divided by 10,000, and so it is going to be 0.0345, or you can say 3.45%. So the chance that you get a defective chip in this factory is about 3.45%. In other words, out of 100 chips, you have a little bit more than 3 chips that might be what? Defective. Okay? So this is what we call total probability. Here is the total probability. Total means it's either from A or B or C. It's the cumulative effect of all of them. So these were some initial topics in probabilities, the definition of that, mutually exclusive, complement, union, intersection, independence, conditional, and total probabilities. And in the next video, we are going to talk about random variables and probability distributions. Thank you so much. We'll see you in my next video.